6.3 is going to be over exponential functions. So first off, if we look at something that has an exponent, like let's say we look at x squared equals 25, we can solve that by square rooting both sides and you get plus or minus 5. But if we change this up a little bit, let's say it's 2 to the x equals 25. It does not make sense for us to, take the x the root. That doesn't make sense. So we have to do something different. And this is called an exponential function. So basically, an exponential is going to be anything of this form, where we have some base, but we have our unknown in the exponent. That's what makes it an exponential, is the unknown being in the exponent. And these change a little different from, like say x squared. 2 to the x is quite a bit different. The actual graph, if you go and graph it of, say, y equals 2 to the x, it looks like this. Everything on this side, that's negative. So let's say, well, let me go ahead and let's make this a function. Let's say this is f of x equals 2x, 2 to the x. So like f of, say, negative 1 would be 2 to the negative 1, or 1 over 2. If we go a little bigger, let's say we do f of negative 5. That's going to be let's go 2 to the negative 5, or 1 over 2 to the 5th, or 1 over 32. As I keep making it a larger negative number, that fraction is going to get smaller and smaller and smaller and smaller, but it's never going to get to 0. So this guy never crosses the x-axis right here. It just kind of levels out. It gets really small. So if we get something like a really big negative number, say like negative 1,000, that's going to be 2 to the negative 1,000, or 1 over 2 to the 1,000, which is an extremely big number. But 1 over an extremely big number is very small, but it is not 0. Okay, so it goes down really close to 0, but doesn't actually go to 0. Okay, so before we get into exponential functions, let's go over the exponent properties real quick. Now, these are things you've already covered and you're already doing, but let's bring them to the forefront just so we can remember them whenever we're trying to solve exponential functions. So let me just go over these. I don't want to spend a whole lot of time on these. If, like, for instance, you're multiplying two things that have the same base, you can combine the exponents by adding them. If they have the same base and you're dividing, we can combine the exponents by taking the top and subtracting the bottom. Let's say we have something, we're raising it to a power, and then we turn around and raise that to a power. We can just multiply the exponents. If we have two things multiplied together, not added, multiplied together, raised to a power, I can rewrite that as a to the n, b to the n. Similarly, if I have it divided, same thing, a to the n over b to the n. Some very handy properties, and I used it on this example up here. Let's say you have a to the negative n. We can rewrite that as 1 over a to the n. And similarly, if you have a whole fraction raised to a negative power, we can flip the fraction and make the power positive. Another good little rule here, if you have something to a fractional exponent, say 1 over n, you can do the nth root of that guy. So like the square root of a, you can rewrite it as a to the 1/2. Similarly, if you have a to the n over m, you can rewrite that two different ways. Okay? We can rewrite this at like this, or we can rewrite it like this. And then another little rule, and then we're going to use this one a lot. If you have, say, this implies if they have the same base, this implies that the exponents have to be equal. Now, we're not canceling. Okay, we're not dividing them out. It just implies that those exponents have to be equal. And our last little rule, which you have to kind of explain because some people forget, is if you have something to the 0 power, it's equal to 1, such that if a does not equal 0. Okay, that rule comes from rule number 2. Look at rule number 2. If I have a to the m over a to the m, everyone agree that's 1 because anything over itself is 1. But rule number 2 says you can take the top and divide and subtract the bottom, and it's 0. So that's where that rule comes from. And then if a equals 0, then right here on that bottom part we would have it equal to 0, which anytime you're dividing by 0, it's undefined. So in this case, 0 to the 0 power is undefined. Okay? Now let's talk about a special case, or a special number. We have a special number we use whenever we talk about exponential growth and stuff like that, and that's e. Okay, e is just a number. It's called a transcendental number. It is approximately equal to 2.71828. Okay, it's kind of like pi. Pi is also a transcendental number. Pi shows up in the ratio of a circle's circumference to its diameter. Well, in this case, e is a number that shows up in nature with anything that has growth. It could be the growth of a population. It could be a growth of a bacteria. It could be the actual physical growth of a specimen. Okay, so anything that has growth, e shows up. And so we're going to use it a lot with anything that has growth. Now, let's do some examples of solving exponential equations. Now, we have better ways of solving exponentials, but let's say we don't know how yet. We're going to learn that in the next section. Let's say I have this guy. Now, I want to use the rule that says this. So really what I need is these bases to be the same. Well, if you look at some of our rules, let's look at rule number 7. If I look at rule number 7, that's this guy, I can rewrite the left-hand side to be 3 to the negative x. Now, the right-hand side, we kind of have to use some intuition on, but 81 actually is 3 to the 4th power. I wanted them to the same base, so I wanted to look at 81 and see if I could write it as base 3. And then now that I've done that, I can use rule number 10 to imply that negative x equals 4, so x equals negative 4. That's our first basic way of how to solve exponential equations, using our little properties we just went over. Let's do another one. This one's a little bit trickier, but not too bad. Can I write these with the same base? Well, if I look at it, one side's base 2, the other one's base 8. So I'm going to ask myself, can I write those to have the same base? Well, you can. You can take 8. 8 is 2 to the 3rd power. So I can rewrite this as 2 to the 3rd power. Now I can combine those exponents by multiplying them. Then I can say that x plus 4 is equal to 3 times x minus 6. And then just solve this guy. Let's see what we get. So we get positive 11. Okay? Let's look at one with e. Let's say I have e to the negative x squared equals e to the x to the 2nd times 1 over e to the 3rd. Now, this is, e's just a number. Just think of it as a number. It's a little bit between 2 and 3. We don't have to get all bent out of shape about it. Just treat it like as such. All the properties still apply. Right here, in the parentheses, we can combine those exponents by multiplying them. So this is just e to the 2x. And then also going back and using, rule number 6, I can rewrite this as e to the negative 3rd. Now I can use our very first rule, rule number 1, to combine those on the right side by adding them, so it becomes e to the 2x minus 3. Because you're just adding a negative 3 or just subtract 3. Then we can say that negative x squared is equal to 2x minus 3. And then I have a quadratic. So we just got to solve the quadratic. So this is x, what is it? Plus 3, x minus 1. So we have two answers. X plus 3 equal to 0. X minus 1 equal to 0. We get negative 3 and 1. Okay? Now, when we talk about exponential growth, we would be remiss if we did not mention compound interest. Compound interest is what banks used to grow interest on a bank account. Here's the formula for compound interest. Let's talk about what everything is. A is the ending amount. That's how much money we're going to have. Basically, I take money, I put it in a bank account, it's going to draw interest. When it draws interest on a certain interest rate, they're going to put that money into the bank account. Then, in the next period, it is going to draw interest on a higher amount, so it's going to grow. So the longer you leave the money in, or the higher interest rate you have, the faster it's going to grow. P is the principal. This is how much we put in. How much money do you put in to start with? Okay? R is the interest rate. Now this is going to be a percent, but we need to change it to decimal form. So if it's, say 3%, we need to change it to 0.03. M is the number of compounds per year. And T is years. Well, it's time, specifically in years. In years. Okay, super important that it's in years. So, for instance, if like it was, 18 months, we wouldn't use 18 for T. We would use 1.5 because that's in years. Okay, so let's do some examples. Let's say you invest $1,000 at 3% compounded monthly for 4 years. How much money would you get? Well, we put it into our formula. 1,000 times 1 plus 0.03. And now M is number of compounds per year. So if it's compounded monthly, there's 12 months in a year, so that's 12 to the power of 12 times the number of years, which is 4. So we would have 1 plus 0.03 over 12 to the power of 48. And we can put that in the calculator exactly like it is. Let me pull my calculator over here, put it in. Let's see here, I have 1,000 times 1 plus 0.03 divided by 12 to the power of 48, and I get $1,127.32. Let's make it 33 cents. There was an 8 behind it, so we rounded up. Okay, here's another example. Let's say how much should we invest to get $6,000 after 5 years compounded quarterly at 4%. Okay, so now I know the ending amount, I don't know the principal. Okay, my interest rate was 0.04. If it's compounded quarterly, that's, every quarter of a year, every 3 months. And so that is going to be 4 times a year. to the power of 4 times 5. So that's going to be 1 plus 0.04 over 4 to the power of 20. Now if I solve for p, it is 6,000 divided by all that stuff. And if you put that in the calculator, we'll see what we get. Let me grab my calculator. 6,000 divided by 1 plus 0.04 divided by 4 to the power of 4. Well, I'll just do 20. I was going to say do 4 times 5, but I'll just do 20. And we come up with $4,917.27. That's how much money we would need to put into the account to get that much back. Now, we have a new formula for continuous interest. Basically, what continuous interest is, well, let's go back to what is compound interest. Every time something's compounded, that means they take the interest and put it in on top of that. But as the more we get, the faster it grows. Well, it gets to a point where they go ahead and change it to what is continuous. So as soon as interest is earned, it immediately goes into the account. And that's where our little e comes into play. Our formula for continuous interest is P times E to the RT, which is super handy. It's actually pretty easy to do too. So let's pick something crazy. Let's say you invested $2,000 at something really high, like 10%, for, let's pick a large amount. Let's pick, because the more time it's in there, the faster it grows. Let's say we do 30 years. And let's say it's continuous, at continuous interest. Continuous interest. So that's going to be 2,000 times e to the 0.1, not 0.01, 0.1 times 30. If I put that in the calculator, I get a pretty crazy number. Considering I put in $2,000, when I put that in, make sure and put these in parentheses when you put it into the calculator as well. Whoops. I'm trying to put it in the calculator. We get $40,171.07. That's a lot of money, considering that we only put $2,000 in. So continuous interest grows faster, and plus if you have a high interest rate like 10% for a long amount of time, like 30 years, it will grow very fast. So that's how we do compound interest, and it is exponential growth. So we'll stop there.